Hello, in the first video about space mapping, we discussed the two of the basic algorithms. The original space mapping algorithm, which utilizes two sets of points in the course and finite spaces to get the mapping. And the other one is the aggressive space mapping, which uses Broyden's formula and a Taylor-based step to predict the changes happening in the fine model parameters. In the year 2000, there was another formulation that kicked in space mapping, and it has been used since then. And this formulation uses space mapping as a surrogate-based optimization. Okay, so what is surrogate-based optimization? You have this is your fine model here. It's an electromagnetic simulation or some other time-intensive simulation that takes a huge amount of time. You give it the parameters, it gives you the response, and the response is accurate. It's called the RF of X. You try to replace the fine model with a surrogate. It's another model. It will hopefully gradually and slowly approximate the response of the fine model, but it's much faster. Taylor expansion of the first order. So if you write that maybe a response, say the response at the point X is equal to the response at the point x naught plus the Jacobian multiplying x minus x naught. This is a surrogate. It's a linear surrogate because you approximate your response through a linear approximation. You can of course build other types of surrogates, maybe use second order information or use a set of points to build a response approximation. There are many such techniques that are called surrogate-based optimization. And these techniques existed before space mapping was introduced. But in the year 2000, space mapping was casted in for the first time in the form of surrogate-based optimization. So what is happening right now is that we are going to be using the mapped course model. So the course model, which is very fast, it's less accurate than the fine model. We are going to map it somehow to obtain a surrogate, Rs of X, that approximates the fine model response. Okay, and we try to keep on improving that surrogate model with with the new data that become available as we develop the algorithm. Okay, so the idea here is we are gonna use space mapping to build a surrogate model, Rs of X, and this Rs of X is gonna be a function of the course model. We'll see how we can really change the course model in many ways such that its mapped response after you make these changes will be approximately the response of the fine model. So Rs of X is approximately equal to Rf of X. So what you're going to be doing after that is that you do optimization on the surrogate model itself. And once you get a new design in the surrogate model, you validate it using actual fine model simulation. If this design is not good enough, then we use the new available fine model data to improve the surrogate model and so on. So this is the algorithm that we can use for space mapping based surrogate model optimization. You start by an initial solution x of 0. So at time 0 you have only one solution. Use the available course model data and fine model data to build a surrogate model at the ith iteration. Okay, apply direct optimization to the surrogate model, and here direct optimization will be fast. Why? Because this surrogate model is based on the course model. I will show you later in the next slides how you obtain the surrogate model from the course model. Okay, once you have the surrogate model, you optimize it to obtain a new point x of I plus 1. You validate this point you call the time intensive fine model and see whether this new design is good enough. And then if your termination condition is satisfied, you stop. Otherwise, you go to step 2. Okay, then you have your new point. You update, you improve your surrogate model again. So hopefully surrogate model now is a better approximation of RF. You apply direct optimization to the surrogate model and then get a new design and so on. And this will continue until you get a design that satisfies your design specifications and whose RF at this point is good enough. It satisfies our given design specifications. The first type of these algorithms is called the input space mapping. And input space mapping means we are going to change the parameters sent to the course model such that it creates a surrogate of the fine model. So this is what's happening here. When you send a vector x to the fine model, you get Rf of x. Okay? We would like to get the same response from the surrogate model. Okay? But here in this case, and this is called the companion model case, we have to add a vector c to x before calling the course model. So we have to change all the dimensions and material properties before we send them to the course model. Okay? So you call the fine model with certain vector of parameters, and then you call the course model with a different vector of parameters, and the difference between them is just the shifting vector c. Another possible input space mapping is to use a full mapping. Okay, so the point x, its response in the fine model is Rf of x. To get the same response from the surrogate model, we have to take x and change it by multiplying it by a matrix B and a vector C. This one has n squared component, this one has n components. Okay, so here you have, these are called the mapping parameters, and this is how you extract them. This expression here is really a multi-point parameter extraction. So you are saying, find for me the matrix B and the vector C such that for the given set of fine model points, you have here k from 0 up to I. We assume that in the ith iteration, we have I fine model points. Make the response of the mapped course model, which is really our surrogate model, matches the response of the fine model. So Rf at any point x of k is equal to Rc at the mapped version of that point. Okay, so we try to extract B and C through all the available points. So this approach is called the input space mapping, and there are two ways. In this case here, B is the identity and the skipped is the identity. Here we allow B to change, and of course this step here is called parameter extraction, and because I'm using more than one point, it's called multi-point parameter extraction. What you're gonna get from here is B and C. Use B and C to build the surrogate model. So this now is gonna be your surrogate model. Okay, you optimize that surrogate model, you're gonna get a new design. You check that design in the fine model, see whether it's good enough or not. If it's not good enough, you are gonna add the point that you have to the set, so this becomes I plus 1, and then repeat the parameter extraction again to get a better mapping. And you keep on repeating these steps until you obtain the desired mapping and the desired response you are looking for. This diagram here illustrates the concept of input space mapping. This is a fine model. You give it the set of parameters, your dimensions, your material properties. You invoke your solver. It takes a huge amount of time. You get the response Rf of x. Okay, but I can't apply direct optimization to this one. It's gonna take very long time. So instead I'm gonna take my course model and create a mapping here before I pass the parameter. So x is gonna come here. It's gonna be multiplied by b, and you add to it c. So you get a new set of parameters, okay? And then you pass this to the course model, different dimensions, different material properties, and you have to find the mapping parameters B and C. There are here n squared plus n unknowns, such that this course model, this surrogate model here, this is called the surrogate model. The response that you get from this surrogate model approximate well the response of the fine model. Once you have this surrogate model, you apply direct optimization to this surrogate model, and then you keep on doing that until your design, the point x you're going to be getting has a good enough fine model response. To illustrate this concept, there were many interesting examples that were suggested over the years, and the target of these examples were to show you that we use space mapping all the time. Really, we have in our brains some course models that we use them all the time in everyday activity. So here this problem is called the wedge cutting problem. It was introduced in 2004 by Bandler and Kozile and used by others as well. The idea here is this is your fine model, this is your coarse model. So the length x is your parameter. So you give your solver x, and the output from the solver is the area corresponding to x, which is shown here in red color. The coarse model, you give it as well x, but the height does not change. Here the height changes. The height here has this expression, 5 plus x over 16, while the height here is fixed at 5, okay? So this one here is simply 5. It does not change. This length here is simply 5. It does not change. While here, you can see the slope, it keeps on changing. It's at x equal to 0, it's 5, but it changes with x. The slope, this expression of this line here is 5 plus x over 16. Okay? This is the expression of this line. So our target is find x such that the area we're gonna get when we cut here is equal to 100. Okay, so the output from our fine model is the area. You give it x, it returns for you this area. Okay, and of course, if you give x to the coarse model, you get a different answer. You get actually a lower answer, because here there is no slope to this line. This line is completely horizontal. Okay, so we're gonna be using in this approach input space mapping. This is our coarse model. We're gonna say, okay, the coarse model is gonna give me exactly the same response of the fine model if I maybe increase x a little bit. So I have to add some c here. C could be usually for the same x, because the area here is higher than the area here. I have to add some increment to the length, to the parameter x, such that I can get the same area as I get in the fine model. Okay, so here I'm going to be using a single parameter extraction. So if I want to determine that shift c in the parameters, I give it the area of the fine model at the given x, and then I try to ask myself, what should be c that I should add to the parameters, the given parameters here, such that the coarse model gives me exactly the same area. Okay, now let's start. Your target is to get an area of 100. Okay, this height here is 5 in the coarse model. So what should be x? Your x should be 20. But this is 20 means that in the coarse model is telling me to get an area of 100, this x must be 20. We call this the coarse model optimum. Okay, this is the coarse model tells us that you have to make x equal to 20 in order to get an area of 100. But here, if you make this 20, you are gonna get a higher area. So we must do some correction somehow to get an area of 100 in the fine model, not in the coarse model. Notice that the difference here in the two models is really not in the speed of the models, but in the accuracy of the model. This is the fine model is more accurate than the coarse model. The coarse model is an approximation of the fine model. Okay, so we start. We're gonna take 20 as our starting point. Why 20? Because 20 is the length in the coarse model that gives me an area of 100. 20 by 5 will give me 100. So we can call this one here xc star. This is what we call really xc star. So here xc star is equal to 20. And this is what we're going to be using at the starting point of the fine model. So now let's see how input space mapping will be applied. Okay, let's follow the steps of what's happening here. We started with 20, okay? This is the optimal coarse model design. This gives me an area of 100. We give this to the fine model gives us 125. Something here is not right, because we are getting higher than what we are expecting. So we ask ourselves now, how should I correct the input parameters to the coarse model to get this area of 125? This is called parameter extraction. So I got now 125, okay, 125 in the fine model. So I'm going to ask myself, This is the response of the course model is 5x. I'm going to say 5x plus c. Okay, and the x here is 20. So I'm asking myself, how should I correct the input parameters of the course model? What is the value of this c, such that I'm gonna get the same response as the fine model? This is parameter extraction step. I'm trying to extract c. If you put this one here, you give 25 on the other side, you're gonna get that c is equal to 5. Okay, this tells us something very interesting, that our surrogate here in this step, I can simply take it as our surrogate at this step is simply equal to 5x plus 5. This is the best approximation the course model can offer now for the fine model, 5x plus 5. Notice what we are doing. We are changing the input parameters to the course model from x to x plus 5. Okay, now we go and apply optimization to this model. What's our target here? This is now our model. This is our surrogate model. Our target is to get an area of 100. Then you are going to set this to 100 to obtain a new design. So let's do that. So I'm going to say here 100 is equal to 5x plus 5. Let's solve that. If you divide both sides here by 5, you get 20. And this is 5 here, so x will be equal to 15. This is our new design. So this is what we get here. This is now the guess that we have for the fine model. So what we built a surrogate model. This is a surrogate model. We optimized it to get an area of 100. We applied optimization to the surrogate model. We got that x should be 15. Now we take this guess, which is coming from the surrogate model, and validate it in the fine model. We get 89.6. So we got lower than the area we're looking for. Okay, we did not really get the 100 we are aiming for. Okay, then we do parameter extraction. We say, how can we make the course model behave like the fine model? So we're gonna do parameter extraction one more time. Then we're gonna write it this way. We're gonna say 89.6 is equal to 5x plus c. Okay, where x here is 15. Okay, so the fine model, when you give it 15, it gives you 89.6. What is the correction we should do to the course model at that same value to give us also 89.6? This is called parameter extraction. The only unknown here is c. Now let's divide both sides by 5 and then subtract from both sides 15. Okay, if you do that, you're gonna get c equal 2.81. Okay, so now our new surrogate model is this model. That the surrogate model, I can write it as rs is 5x plus 2.81. Okay, 2.81. Okay, now you are gonna do again optimization on this model. This is now my model. This is an approximation of the fine model. We're gonna set rs again to 100. I want to get 100. And the new x you're gonna be getting in this model is 17.19. Okay, you repeat this again. You calculate the fine model as 17.19. You obtain 104.4. But this is higher than 100 that I'm aiming for. Then I'm gonna say here 104.4 is equal to 5 multiplying 17.19 plus c. What is c? What should be the extracted c such that the course model gives me 104.4? Okay, add this x. I solve for c, I get 3.69. Okay, and now this is now my new surrogate model. It's gonna be 5x plus 3.69 as shown here. Okay, I optimize that surrogate model again. So I equate this number, which is, I'm gonna write it here somewhere. It's 5x plus, we agreed this one is 3.69 here. I'm gonna say this is a surrogate model. I'm gonna say this should be equal to 100. I solve now for the new x, and you divide by 5 and so on. You get x equal to 16.31. This is now our new design. You validated in the fine model, get 98.16. Then you ask yourself, what is the correction I should make to the input parameters of the course model such that it gives me also 18.16 at this input parameter. So I'm gonna write here 18.16, 98.16 is equal to 5 multiplying 16.31 plus C, and then I solve for C. You get C is equal to 3.32. So this is the mapping that you have to do, the correction you have to do. And now if you optimize this surrogate model, you get this answer, which gives you a fine model point of 100.76. This is very close to the 100 we are aiming for. So you see, we're able to optimize the fine model by repeatedly using the coarse model as a surrogate and extracting different C at different iteration using the information that becomes available. Okay, and then so we extract C and then we apply optimization to get a new X. We extract C, we apply optimization to the surrogate model to get new X, and so on. One other example which was also tried in this using input space mapping is a two-section impedance transformer. Again, both models are simulated in MATLAB. This is transmission line, okay, and this is a transmission line model. Both have characteristic impedances Z1 and Z2. What you do here, you include some capacitive loads. So this becomes your fine model. This becomes your coarse model. Your parameters are L1, L2. Because of these capacitive loads, the response of the fine model and the coarse model are different. Okay, so what you can do, you can apply some correction to this vector x, which is L1, L2. So you can shift it by a certain amount, or you can multiply it by a matrix B and add a vector C, such that when you pass it to the coarse model, it gives you the same input impedance as that obtained from the fine model. Okay, so it's the same concept, but it's applied to a more practical high frequency impedance transformer. And here I'm showing you, and this is taken from the notes of Dr. Slavomir Kozael. I'm showing you the response at 3 different points. X, this is L1, L2, 90, and 90. This is here, I believe these are electrical degrees. So the blue line is showing you the fine model response at this point, and the black line is showing you the coarse model response. Okay, so the coarse model and the fine model give different responses at different points. However, if we take the parameter x, the vector parameters x, which is L1 and L2, multiplied by this matrix B, and add to it this vector C, and then after you get this new mapped parameters, you call the coarse model simulator with these parameters, you will see that the fine model and the coarse model are identical. Okay, so I could use this mapped coarse model here, okay, and this is called the input mapping because I map the input parameters. I can use it to replace the fine model, which could be more accurate or more time intensive depending on the case. Another type of space mapping, again, space mapping as a surrogate model, is called the output space mapping. In output space mapping, they say, okay, the coarse model and the fine model do not give us the same response. So why don't we try to correct the response directly? Don't change the parameters, but add a vector D to your responses. This vector RC could be, for example, the S parameters at different frequencies, or it could be the torque, electric torque at different electric angles. Okay, so notice I'm not trying to change X anymore in the coarse model. I'm trying to change RC of X. I'm trying to change the output of the coarse model by adding a vector of responses. You can have it as an additive output space mapping or as a multiplicative output space mapping. So you can multiply, you calculate the coarse model response, multiply it by a matrix A, and add to it a vector D. This matrix, of course, here we have, say, M responses. So this matrix is going to be M by M, and this vector is M by 1. How do we get A and D? We get A and D simply through a parameter extraction step. We ask ourselves, what is the best A and D? Remember here, this is a vector of M unknowns. This is a matrix of M squared unknowns. So we have here M squared plus M unknowns in general. How do you find A and D such that when we map the coarse model in such a way, its response will match the fine model point for a set of points. And here we assume that at the ith iteration we have I points. So in general, we can use up to I points in this mapping. So this is a multi-point parameter extraction. I can do it, of course, using only one point, and this will be called single point parameter extraction. We can do it for both. So for output space mapping, this is really what's happening. This is your parameter x. You give it your time-intensive accurate model. You get your vector of responses. Here you take the same parameter x. I'm not gonna change x. I pass it to the course model. The course model will give me here RC of x. And then I take the output and I change it. I change it by multiplying it by a matrix A and adding to it a vector D. And as a result, I'm going to get a new response RS of x. By properly selecting A and D, I can make this surrogate model response matches in a reasonable way the fine model response. So this is called the output space mapping. And it's another valid approach for applying space mapping optimization. We're going to repeat again the wedge cutting problem using output space mapping. So this is the RF. This is the fine model response. Again, it is a wedge with a slope. And this is the rectangular piece, okay? This is the course model. Here the top line doesn't have a slope. We start from 20. This is the optimal course model design. We send this to the fine model, we get 120. We ask ourselves the question, okay, the course model at this 20 is gonna give me 100, okay? But the fine model is giving me 125. So the course model at 20 will give me 100. But the fine model at the same 20, if you substitute here for 20, you get 125. So I ask myself the question, how should I correct the fine model response, the course model response, in order to get that same response? So I'm going to say here 5, okay, so I can write it here. So I can say 125 is equal to 5 multiplying 20 plus D. How much D? What is the value of D that should add to 5x at 20 such that it gives me 125? If you do this calculation, of course the answer will be 25. So your first extracted D is 25. Then I can simply say here, then my surrogate is equal to the course model response, and I'm gonna add to it 25. Now I go and I optimize this. Okay? I'm going to optimize this. So I'm going to optimize, by optimizing it, I'm going to say 5x plus 25. What is my target? I want to get an area of 100. So I'm going to say this is equal to 100. Okay? You now solve for x to get a new design. So you get x equal to 15. Okay? And this is what I have here. Solve this one, you get x equal to 15. You check, this is obtained from the surrogate model. This is now our surrogate model, 5x plus 25. You check it in the fine model, you get 89.063. So it's not really the 100 we are looking for. Then we have to do a second step. Okay, how do we do a second step? We ask ourselves, what is the D that I should use in order to make the course model gives me at this point, which is 15, 89.063. I'm trying to make the course model behave like the fine model. So this is the equation I'm gonna write. I'm gonna write here 89.063 is equal to 5 multiplying 15 plus D. I now want to extract a new D, a more accurate D. This is 75, you move it to the other side, you obtain 14.063. This is what we have here. So now our new surrogate model is RC of x plus 14.063. You go again and apply optimization. So you say, and I can write it here on this side, okay? We don't have big room. I can simply say 100 is equal to 5x plus 14.063. And then I attempt to solve this equation. If you solve this equation, you obtain Okay, so move 14 to the other side. So you're gonna get something like 85 point something. You divide by 5, you get 17.188. You pass this new design, you have to validate it in the fine model, which is this one. You obtain 104. So we went a little bit above 100. You ask yourself, how can I make the course model gives me 104.401 at this point? What would be the D that will make the course model gives me 104.401 at 17.188? Okay, you do this extraction, you obtain this D, and you keep on repeating these steps over and over again. This is the last two steps. You can see the fine model is oscillating between 100.76 and 99.68. So we are very close to the design we want to get. So what we did here is that we use the course model. We used the course model. We extracted a surrogate for variable D. D changes from 25 to 14 to 18 to 16 to 17 and so on. And then I apply optimization to this surrogate model. So I equate 5x plus D to 100, and then I get a new design. This approach really summarizes the concept of output space mapping. There are other types of space mapping that I'm going to illustrate as well, but this wedge cutting problem is illustrated here in this section only for the input and output space map. Also, in the year 2000, the concept of the input space mapping was implemented using artificial neural networks, and this was the work of Jose Raya-Sanchez, who was a colleague of mine of McMaster's with this Raya-Sanchez. So the mapping does not have to be linear. It could be a neural network. You give it X, it's gonna map it to some Y of X, such that this mapped course model is going to give us the same response as the fine model. So here our unknowns are the weights of the neural network. And those who know the theory of neural network, it has lots of weights inside. We can optimize for them as well. Okay, and of course you can move the neural network to the front of the course model, and this becomes an output space mapping. Here I'm changing the input, so this is an implementation of input space mapping. Okay, I'm showing you here only three references related to this specific lecture. There are, as I said, many other references and work done by Professor Bandler from McMaster University, Professor Slavomir Kozael from University of Reykjavik in Iceland, and many others in space mapping and its applications. But these three publications are related to the current presentation, and I'm putting them there for you to use them in your project. But again, those who want to read more about the subject, you can do an extensive literature survey, and you'll find probably hundreds of publications written about space mapping, its theory, and its implementation.